And welcome back. As we go ahead and continue looking at binary search, let's go ahead and take a discussion to look at the efficiency of that algorithm that we have developed. So with binary search, one thing to keep in mind is that the algorithm is extremely fast compared to an algorithm that simply tries all of our array elements in order, such as a linear sort. In the binary search, you eliminate about half of the array from consideration right at the start, because we know it's either in the front half or it's in the back half. And then once we've done that, we can say, well, we're going to eliminate that down to another quarter, then an eighth of that array, and so on and so forth. These savings can add up really, really fast and make us a really fast algorithm. So, for example, we have an array of 100 elements. The binary search will never need to compare more than 7 elements to the key. A linear search could compare as much as 100 elements. And on the average, will compare as much as 50 to that same amount. If we want to continue to talk about searching array, we can make this even more drastic. So let's just say the array is even larger. We can see even much more drastic savings as this set gets larger and larger. So for example, if you have an array with over 1,000 elements, the binary search will only need to compare about 10 array elements to that key value as compared to an average of 500 for a serial or a linear search. Now, due to its nature, the one thing you might notice is with the binary search algorithm, it's always going to work within powers of 2 to find the maximum number of comparisons. So, as, for example, if you have that 1,000 elements with 2 to the power 10, it's about 10 to the 24. So it's always going to kind of follow with that. Similar when we had, if we had, go back here real quick, and we talked about the 100 elements here. Well, we're saying, okay, that's 2 to the power 7. So that's how we kind of know where that's going to be, because what's 2 to the 7th? 128. Now, the thing with all this numbers, because we start talking about powers and exponents and stuff like that, well, the binary search algorithm has what we call worst case runtime that is very logarithmic because we're operating under those powers of 2. And the way we would express that is big O of log n. Now, if you compare this to a linear search, you're going to find that this is big O of n. So let's take a real quick note on big O and how that is handled. So big O notation is one of the measurements that we can use to determine how efficient an algorithm is. The faster the curve grows, the worse the algorithm. Big O of 1 is kind of the ideal time because it means that no matter what your data size is, you're going to have a constant amount of time to solve that. If you look here on our curves, though, you can see, for example, we have big O of log n right here. It starts off maybe not as efficient, like you can see later down here with really small sets might be faster, but as our data sets get larger, you can see how it really kind of tapers off and plateaus in comparison to something like big O of n, which is much more linear, or n squared, n cubed, or n to the power of n. All right, anytime you start getting into more exponential like this, it's going to have a lot more issues with efficiency. So let's look at this binary search applied into a specific example. Let's say we want to find a file. So this next program we're going to look at is an example where a recursive solution is much easier to write and understand than that of an iterative solution. Consider the problem finding a file buried somewhere in your computer. And so, for example, if you're using the Windows file system, let's say you have the following file and directory structure on your hard drive. So it's going to have, let's say, C:, Java programs, recursion, find file, etc. You can have homework, test Java. You have another layer called papers. There's a lot of stuff here, even in this little example. Obviously, there'd be a lot more on here, but this is just an example of how the structure might be. Well, how do we know where something is? How can we find the location? Let's say we want to find a location file given its name. So let's say on that previous thing, we had termpaper.odt. We'd like to know whether or not that is in C:papers. So we want to say, hey, we're going to say findfile.java. This is the name of our class. And we want to know whether or not, for example, if that is in the Java programs / recursion. So our general solution, regardless of which file we're looking for, is to start at some root directory, such as the C drive, and then go through all the items in that directory. Now, if an item is a file, we're going to check to see that it matches the particular target. If an item is a directory, then we're going to make a recursive call to restart that search using that directory as the new root directory. So let's look at a quick pseudocode of our recursive solution. So we're going to search for the file based on a current path and a target file. If the current path is not the directory, we're going to return an error. And for every item in the current path, we're going to first check to see if it's a directory. And so then we'll have a recursive call to search for the file. And then, of course, again, we use I in target file to look to see if it's there. If R is a successful match, we're going to return R. Then, of course, we jump back. We have if I is then a file, not a directory, we can see if it matches the target file. If it does, return the passive file. And ultimately, if neither of those work, we can return target not found. So, jumping back to finding the file, if we want to implement this algorithm, we need to find a way to determine if path is a directory or file, and we need to find a way to get all the items within a directory. Java's file object will actually do all this for us. So to use it, of course, we have to import it using java.io.file. And of course, just real quick, here's those relevant constructors and methods that we might want to use. So we, of course, we have the file constructor. We have a string called getAbsolutePath, which allows us to return the path name of a particular file. We have a string called getName, which allows us to return the name of that file. We have a Boolean called isDirectory, which actually allows us to test whether or not something is a directory. And we can use the file list files, which of course allows us to return an array of file objects within that directory. So let's actually implement our algorithm now. So using the file object, we can implement the recursive algorithm to find a file. The implementation in found file is going to return an empty string if the target file is not found. If the initial folder supplied is not a directory, well, then we're going to get an error message. The sample results that we might get would then assume, of course, our program runs using a directory structure. If we don't have a directory structure, maybe we're not in a Windows machine, for example, and maybe we're in some other type of operating system, that means we, of course, would then have to do some different assumptions in writing our algorithm. And here is our code. You can see we have this search for file right here. And, of course, we can see we are looking to see if it is a directory here. If it is, of course, not going to be, it says if it is not a directory, we return. Otherwise, we're going to search that directory, we're going to first look to see if it is a directory, so we're going to recurse again. Otherwise, of course, we can work through this to find out whether or not it is empty. And we can, of course, down here, check for that match to see if it is the actual file name. And if there's nothing, we're simply just going to return an empty string, because what type do we have here? We have a string because we're trying to find that file name. So if we look at our main, we of course have a file root folder equals new file n. And notice I do have a note here that says change this to the file path we want to search. So this is going to search a local network drive they have here on this computer. And then down here we have our string result, which is going to store that value of where we find that file. And when we say as long as the result is not empty, all right, we can of course print it out. Otherwise, we're going to say the file is not found. So all I'm going to go ahead and do is give this a quick run. And right now it's looking at this network drive, and it's going to look to see whether or not this file exists. So I'm going to tell it, go ahead and look in the workspace folder to start. And it's going to go ahead and run, and this might take it a few minutes, so I'm actually going to pause the video while it runs in the background here, because it's going to go through each of those files and look for them. And you can see it went ahead and returned that file path. It told me exactly where I could look to see where that is. Even though I told it start in workspace, you can see that it went ahead and recursed to go ahead and find where that file is located. So that was very helpful. And now if I wanted to find that, I could go ahead and navigate in my folder directory to go ahead and find that. But again, this is just another example of the binary search algorithm and how it could work. If I were to do this with a linear search, it would take much, much longer.